Assalamualaikum. Today I will present about the Lummus slash UOP classic styrene technology and Lummus slash UOP smart styrene technology. My name is Muhammad Izzat bin Ramli and my metric number is 33DPE 1851020. The introduction. The first point is styrene monomer (SM) or vanillin benzene is an important industrial chemical used in the manufacture of variety of polymers. The activity of the vinyl group makes SM easy to polymerize on its own or with many other monomers. Commercial processes for the production of styrene by the dehydrogenation of ethyl benzene. The second point, the dehydrogenation of ethyl benzene were developed in Germany and the United States in 1930. The demand for synthetic rubber during World War II resulted in a large boost in production, and a growth in the use of styrenic polymer has continued to fuel demand. The history of uh, the process is the first process, classic SM process, was put into commercial practice in 1972. The second point has been selected for more 50 major projects. The second process is smart SM process. The first point is the first commercial on stream was in 1995. The second point is award total of 5 projects. Next, process perspective. First, Lummus classic styrene technology. The Lummus styrene technology was first put into commercial practice in 1972. The unique dehydration reactor system is designed to operate at minimum economical operating pressure to achieve the highest hensem selectivity at high conversion. Since its introduction, the technology has been selected more than 50 major projects. 42 plants are currently in operation. The technology uses commercial iron oxide-based dehydrogenation catalyzed in two high-temperature adiabatic reaction stages. Interstage reheating is required because of the endothermic nature of the dehydrogenation reaction. Reactor temperatures are maintained by heat exchange with superheated steam, which is used subsequently as coffee up to the reactor. The second is Lummus Smart Styrene technology. The process is uniquely qualified for increasing the capacity of existing plants at the lowest investment. The combination of higher ethyl benzene reheat convention and interstate provided by the oxidative reheat step result in the constraining debottlenecking the usual equipment fractionation and steam superheated system to provide more than 50% additional capacity. The introduction of oxidative reheat eliminated the indirect reactor reheat equipment, simplifying the steam superheated system, and significantly reduced the benzene recycle because of high the benzene conversion per pass. The permit a significant expansion of plant capacity without the need to replace major and expensive equipment, such as the steam superheater. The waste heat exchanger on the heat reactor influence stream the off-gas compressor and the ethyl benzene or styrene monomer splitter. The lower ethyl benzene recycle flow rate reduce utility consumption. Process description. This is a classic styrene technology flow diagram. This process, ethyl benzene and a portion of steam are combined and superheated. The EB steam mixture is combined with additional superheated steam and dehydrogenated in multi-stage radial flow catalytic reactor system. The hot reactor effluent is cooled and condensed in a waste heat exchanger to recover the heat. The gas are compressed and then treated to recover hydrocarbon prior to being fed to the fuel gas system. The liquid are separated into aqueous condensate layer under the organic hydrogenated mixture. Next, the product Sm is separated from Dm by fractionation. After that, the Dm is first distilled in Eb or Sm splitter to take Eb and lighter component of it. The Eb or Sm splitter overheat is fed to the Eb recovery column, where byproduct benzene and toluene are separated from Eb. The Eb stream is recycled to the dehydrogenation reactor. The Eb recovery column overheat stream is further split into useful high purity benzene and toluene byproduct or sent to the adjacent refinery as benzene toluene mixture. After that, Eb or Sm splitter bottom are fractionated in the Sm finishing column, which produced Sm product are overheat and a very small amount of tar as bottom. The tar normally used for food in the steam superheat. The first figure is smart styrene reactor system. The process is identical to the classic SM scheme. It's a multi-stage radial flow catalytic reactor system contains two catalysts, as conventional ethyl benzene dehydrogenation catalyst and an oxidation catalyst. Hydrogen formed from Eb to Sm endothermic dehydrogenation reaction is reacted with oxygen over a highly selective catalyst. The removal of hydrogen from the process substantially increases single-pass ethyl benzene conversion while maintaining high Sm selectivity. The heat is used to reheat the reaction mixture and to avoiding expensive interstage heat exchanger equipment. The hot reactor effluent cooled and condensed in a waste heat exchanger to recover heat. The gas are compressed and treated for hydrocarbon recovery prior to sending to the fuel gas system. The liquid is separated into aqueous condensate layer and the organic dehydrogenation mixture. The separated of product Sm from Bm, and all steps thereafter are the same as in the classic Sm process. Process chemistry. The first is classic styrene process. The major reaction in the classic styrene process is the dehydrogenation of ethyl benzene to styrene monomer and hydrogen. Side reaction produce benzene and toluene and some light compound. The reaction are represent just like in the picture. The second is smart styrene process. The major reaction in the smart process are the hydrogenation of Eb and the subsequent oxidation of hydrogen. Produced in the first reaction, the hydrogenation side reaction produce benzene and toluene and some light compound. The reactions are shown in the picture.